In this series, we're building up a small 1-bit computer on the breadboard, and we're basing it around the Motorola MC14500, which is a little 1-bit microcontroller. It's a really interesting design, and we've been following along with this minimal ICU system that we found in the MC14500 handbook. And I think we're nearing completion, or at least I hope so, because we're almost out of room on the breadboard. But according to that minimal ICU system diagram that we've been following along with, there's just one component left, and that is the scratch register. So that's what I want to tackle today. I want to take a look at what the scratch register is, how we can tackle it, and then put it on the breadboard itself, and then write a program to hopefully test it all out. And fingers crossed it'll work. Who knows? So let's hop over to the bench and get started. All right, here's our minimal ICU system, and we've been mostly following along with it. Some of the things we've done a little differently, like the reset circuitry here and how they're handling some of the chip select over here. But for the most part, we've been following pretty closely to this. And we actually have everything built except for this little piece right down here in the middle. This is called the scratch register. And what sets this register apart from the output register and the input register next to it is that it can do both writing to and reading from. So from the input, we can only really read what the inputs are. We can't store anything into the input. And we can only store information into the output. We can't read what is stored on the output. But with the scratch register, we can do both. And so that gives a little bit more flexibility to this total system. And the chip that they're using for this is the MC14599B. It's just an 8-bit addressable latch, but it has one really unique feature that is going to cause us a little bit of a headache. If we look right down here, we can see that we have 8 latches and a 3-bit decoder that allows us to select one of those 8 latches. And then depending on whether we're writing or reading to the chip, we can either store 1 bit into those 8 latches through the data pin, or we can have whatever is stored in that latch output onto that data pin. So our data can go both directions through this. This is a really nice feature that allows this chip to be used both for writing to it and reading from it. Now, I don't have any of these MC14599s, and so instead I'm going to use the 74HC259. It's also an 8-bit addressable latch, but unlike the Motorola chip, we can only write to this chip. We can't actually use it as a demultiplexer to put whatever data is being stored in it onto a single bit back out onto that 1-bit data bus. And we actually use this same chip for the output register over here, and it worked fantastically. But since we also want to be able to read from it, we need some way to take these 8 data bits here that are going to show the information that's stored in it and output them back onto the bus. So we need another chip that's going to be a multiplexer, essentially. And it just so happens that we've used a multiplexer in the past, the 74HC4051. This is a fairly simple chip. It just takes 8 bits on the way in, and then you have a 3-bit address that selects one of those 8 bits and then dumps it out onto a single common pin. And we actually use this for the system inputs. So we're going to use a combination of what we used for the input and what we used for the output to create a register that we can read from and write to. So what's the best way to hook these two chips up so that they will do what it is that we're asking them to do? Well, I have a little schematic here that we'll take a quick look at. And essentially, there's just an 8-bit bus that's shared between the 259 and the 4051. And then we have data going into the 259 and data coming out of the 4051, depending on which write or read pins are selected. And we're going to use the 74HC00 to help us with that control logic. So this looks like a pretty simple setup here, but looking at the pinout of the two chips, I think it might be a little bit of a headache to hook up. But we'll give it the old college try, so let's go ahead and pull that breadboard out and get to it. All right, and so here's our breadboard where we left off last time, and we're really running out of space here. So we've only got this little space here in the bottom right. But I think we can stuff both chips in here. So let's go ahead and get those chips in place. We'll start with the 74HC4051. And then we'll pop in the 74HC259 here. All right, and then we'll get power and ground for each one hooked up. And then if you remember on 4051, pin 7 also gets pulled to ground. And we can actually see that right over here. So we'll just go ahead and copy that as well. Now things are going to get pretty hectic because we have a whole lot of things that we need to stuff in such a tiny area. So I'm going to go ahead and get the biggest obstacle out of the way, which is going to be the LEDs. And we need to stuff 8 LEDs in here. So that's pretty tight, but I think we'll be able to stuff them in. All right, not super graceful, but I think it's gonna work. Now we still have to hook these LEDs up to something, and they need to go to the 8 bits that are going to be shared between the two of these. But for the moment, I'm just gonna pull them off of this 74HC259 here. And the 259 has 4 bits on the bottom and 4 bits on the top. All right, so here's where things are gonna get a little hectic. The 8 bits that are hooked up to our LEDs here is that kind of pseudo 8-bit bus that needs to go in between the 259 and the 4051. Now the 259 is pretty nice. The 8 bits are set up in a relatively logical manner. It's the 4051 that's causing all of the trouble here. First things first, the actual 8 bits that go into the 4051 here are not next to each other in any way that kind of makes sense. They are pins 1, 2, 4, 5, 15, 14, 13, and 12. Now that 15, 14, 13, and 12 sounds nice. Hey, yeah, those will be in order, right? No, not quite. Bit 0 is on pin 13, then bit 1 is on 14, bit 2 is on 15, and then bit 3 is all the way back down again at pin 12. Bit 4 is on pin 1, bit 5 is on pin 5, bit 6 is on pin 2, and then bit 7 is on pin 4. So the order doesn't really make any sense, but we need to get this really ridiculous order to hook up to this kind of logical order over here. And so this is going to require a lot of jumpers, crissing, and crossing. So there's really only one way to tackle this, and that's just 1 bit at a time. So we'll start with bit 0 and work our way up from there. So that's the first 4 bits hooked up, but now it gets a little confusing because bit 4 all the way over here needs to come all the way over to this pin, and it gets a little wild over here. So again, we'll just do them one at a time here. All right, it's not just these 8 bits that are shared between the two. We also share the data pin as well as the 3 address select pins. And of course, they're not in convenient spots either. So we'll just take them one at a time again, and we'll start with the data pin, which is pin 13 on the 259 and pin 3 on the 4051. And then our 3 address pins. On the 259, that is going to be pins 1, 2, and 3. And on the 4051, that is going to be pins 11, 10, and 9. Well, we already got a ton of stuff here, but actually I think this might work out because we can run some jumpers over the top of that and use that to kind of hold everything in place. There we go. It's not graceful, but it looks kind of cool, I got to admit. All right, so we've got everything kind of shared between here, but we also need to take these 3 address pins and get them up to our address select, which is coming down through here and over to here. And we also need to take that data pin and hook it up to that 1-bit data bus. And so I'm actually going to borrow all 3 of those off of this 4051 that's over here. There we go. Now we've got the majority of all this hooked up. We've got our 8 bits shared between the two. We've got our 3-bit address coming in as well as hooked up to the primary address here, and the data bus is shared as well. All right, so we have the bulk of it done now, but we're just missing the control logic that will allow us to either write to or read from the scratch register, as well as the chip select that will define whether we're selecting the scratch register or we're selecting the input and output. And so to select the 4051, we're going to need 1 NAND gate, and to select the 259, we're going to need another NAND gate. And that's pretty fortunate because on this 74HC00 over here, we happen to have 2 spare NAND gates that we didn't use. So that's great. We can borrow those 2 NAND gates there. But we also need an inverter. And that's because when the chip select line, which is all the way up here, is high, that's when we're selecting either input or output. But when it's low, we want to be selecting our scratch register. And so what we need to do is we need to invert that chip select pin. And it actually just so happens that we have a 74HC00 all the way up here that's only half being used. There's actually 2 spare NAND gates on this. And it also happens that the chip select line right here is available right here. It's a little hard to see, but it's actually already on here. So we just need to borrow that and invert it and then get it all the way over to down here. And that inverted chip select is actually going to be an input into both of our NAND gates down here. There we go. So now we have our inverted chip select coming all the way over to here to be inverted, and then all the way down to here into the input for both of our NAND gates. All right, and so now the only 2 connections that we need to make are the 2 remaining connections for our NAND gates here. And one of these is going to be the write signal, and one of them is going to be the inverted write signal. And it just so happens that we already inverted the write signal using one of the NAND gates on this chip for the input. And that's going to be this little wire coming in here. So this is going to be our write, and then this little gray jumper that comes out of the side here is going to be our inverted write. So I can just borrow that inverted write signal there. And then this NAND gate on the bottom needs the non-inverted write signal. Well, the non-inverted write signal is available on those inputs. So we'll just run another little jumper right across the top here. Now we need to get the 2 outputs from these NAND gates over to the chip enables for both of these chips here. And starting with the 4051 here, the chip enable is pin 6. All right, so that's the 4051 taken care of. And then we got to do the 259. And the chip enable for it is on pin 14, which is way up here. And we need to hook it up to the output from our NAND gate down here. All right, and then the final piece of the puzzle is whenever we hit our reset button up here, we want to clear out the 74HC259 here. And the clear pin on it is pin 15, and we happen to have our reset signal on this far rail over here on the right. All right, I believe that's everything hooked up correctly, or at least I hope it is. It looks certainly epic, and we are completely out of room. This thing looks absolutely wild. But does it work? Well, actually, I don't really know at the moment. So all we can do is just plug in some power and ground and see what happens. All right, something's happening. Interestingly, we've got 1 bit of our scratch register illuminated here. We've got 2 bits on our output register illuminated here. And the program is running through doing something. It hasn't halted itself yet, at least. But it just loaded in a bunch of random data. If we hit reset, it should clear out both of these. So we'll see if at least, yeah, there we go. All right. So at least we know that the reset is working. And so the only way to test this is to write a program that tests essentially every function of the machine on our breadboard. All right, I've got a program saved into our RAM chip here that I think should test every aspect of the system. You can see I've got some equivalent of what the program's doing over here. It's not a particularly useful program, but it should test everything at the very least. So you can see on one of these examples, we have the input coming in, goes through an inverter, coming out of that inverter goes into an XNOR gate, and then the other input to that XNOR gate comes from a shifted bit that's 1 step over. And so this is something that should use both the input, the scratch register as both reading and writing, as well as storing a result in the output. So we'll step through the program 1 step at a time here just to see how it goes. And our first step is 0110. And this just forces a 1 into our result register, which we can see here as this little yellow LED. So now we have a 1 in our result register. And then we use this 1 to initialize both the input enable register and the output enable register. So now that both of those are initialized, we can pull data in and put data out. That was pretty important, but that's our basic setup. So here's where things get interesting. We're going to load, which is 0001. And we have the chip select bit set to 1, so that's selecting our input and our output. And we're loading from position 001. And so if we look down here, address 001 is the second switch on our little dip switch here. And so we can see that's set to a 1. And so yeah, we loaded a 1 in. Now we're going to store the inverse of that into our scratch register down here. And that's what this step is. It's 1, 0, 0, 1. Now, the inverse of 1 is 0, so we stored a 0 in our scratch register. So we can't see anything. All right, so let's go to the next step here. So again, we're going to load, and we're loading from input, and this time we're loading from address 010, which is switch number 3 down here. And that's a 0, and so you can see that our result register is now 0. And then we're going to store the inverse of that in our scratch register. So if this works, we should see one of these LEDs illuminate. Yeah, look at that. All right, so we're able to write to our scratch register. Now that I'm looking at it, I can see that we have the same problem with our scratch register that we have with our output register up here, and that's that the least significant bit is on the far left, because we wrote to address 010, which should be the third LED, and you can see it's third from the left, but our program counter over here and our address over here is all done with the least significant bit on the right. So we've got some things backwards here, but we'll keep that in mind and we can work around it. All right, so the next step is just repeating the same thing. So we're loading, and then we're storing the inverse of that into the scratch register, and then we're loading, and we're storing the inverse of that into the scratch register. So now we've loaded a 4-bit number and stored the inverse of it into the scratch register. So you can see that we have, down here we've got 1, 0, 1, 0. And then if we start from the left side here, we've got 0, 1, 0, 1. And I'm not actually writing anything to this 0, 0, 0 address here on both the output and the scratch register here. I'm not going to use that bit. And so, yeah, so 1, 0, 1, 0, and the inverse of that is 0, 1, 0, 1. So we were able to load something from our input, invert it, and store it into the scratch register. So that aspect of it is working beautifully. Now, can we read from the scratch register? And so this next step is a no operation. I forgot I put that in there. So the next step after this one is a load. All right. So 0001 is a load, but our chip select is 0. So now we're loading from the scratch register, and we're loading from address 001. So 001 is going to be this second LED, which is a 0, and you can see our result register is 0. So hopefully what that means is that we successfully loaded a 0 into our result register. Now we're going to XNOR that. So 0111 is our XNOR operation, and our chip select is 1, so that's going to be our input. So we're XNORing with our input from address 100. And 100 is going to be the fourth one down here. And so that one's set to 1. And so we stored a 1 in our result register, and the next step is to put that 1 into our output register here. And you can see that it stored it. Again, our least significant bit's on the left, and I'm not using this this leftmost LED here. So it did put it in the right place. So that's awesome. That means it worked. That's crazy. That's super cool. So we were able to load and write something. All right, so well, let's just let it go. There we go. It ran to the finish. So you can see our output is 1111. And if we look at our kind of mock-up logic diagram that we built earlier, you can see that with an input of 1010, our output is all ones. All right, so that worked awesome. That's super cool. And we hit a 1111, so we halted, so our halt is still working correctly too. This appears to be working perfectly. That is epic. All right, but there's a little voice in the back of my head saying maybe you totally messed up and it just wrote all ones to the output as a fluke. So let's try a different input and see if we get the correct output out of it. And so if we do an input of 1001, we should get an output of 0101. So let's reset this and let it go. All right, so that was our inversion that happened there. Yes, look at that, 0101. It did it correctly. Oh, that is so cool. All right, let's try one more input here. Let's do 0111 as our input. All right, so let's reset this again. Let it go to town. All right, there's our inversion. Yeah, so 1100, that's correct, 1100. How cool is that? It's working correctly. All right, let's try one more thing. We're gonna do this, but we're gonna put the speed at max. See how quickly it can burn through this. Oh, that was cool. How cool is that? Let's do it one more time. And you gotta remember, this is running at an incredibly slow clock rate ultimately, because the MC14500 can run at up to 1 megahertz. And this is probably only at maybe 1,000 or 2,000 hertz. It's really, really slow. So that's, how cool is that? So there we have it. We've completed every aspect of the minimal ICU system. This is technically a fully functioning computer. We're able to read input, we're able to stuff that input into a temporary place, read back from that temporary place, do something else with what we read back, and then store that in an output register. So we're doing proper real calculations here. We built a computer. It's the most useless computer on the planet, but it's our computer, and I love it. So for all intents and purposes, this thing is finished. It feels weird to have a project and say it's finished, because anybody who has a project knows that it's never really finished. There's always something you want to do. And actually, if I were to do anything to this in its current state, all I would really want to do is switch my output register LEDs and my scratch register LEDs. So the least significant bit is on the far right. But we've hit the limits of what we can do with this breadboard setup. Obviously, it's chock full from top to bottom. But what this means is that there's no room for expansion anymore. I mean, sure, I could stick more breadboards off the side, but if we're going to put breadboards coming off the side and expand this further, I think there's some fundamental changes that I want to make. But thinking about those fundamental changes and where we're going to go from there and what the next step is all something for a different day. So instead of thinking about the future, let's just revel in the glory of the present. And I'm going to sit down and play with this and try to come up with more interesting programs, because I'm just really happy with the flashing lights. So thank you guys so much for watching, and we'll see you in the next episode.